To be honest, this whole left and right sums is a little bit confusing even to me as a teacher. I mean, like I understand the material, but I had to really put some thought into it every time that I'm going to be doing a problem. And to avoid this, and I did mention that we were going to be moving on to the generalized version. It's like, all right, well, I don't want to know how to do the sum or the addition for like four particular rectangles and for five particular rectangles. We saw that if we increase the number of rectangles, the area seems to become more accurate. So why not just let the number of rectangles go to infinity? If we do that, then that means that we created infinitely many rectangles. And what happens? Well, if you notice, if you have more rectangles, what's happening with delta x? The more rectangles that you have, the smaller delta x becomes, right? So now you can either have n going to infinity, which is equivalent to me saying delta x going to 0. So if we theoretically let that happen, and our delta x, how do we calculate delta x? Well, we still do the b minus a over n, and remember, n is a number of rectangles, not what interval you are going to. Okay, so now let's do this theorem. Let's actually do a problem when we don't have to actually do some individual calculations, but it does require us to remember some other formulas. So theorem limits of lower and upper sums. What is the theorem of limit of lower and upper sum? It's pretty simple. It's saying whether I take the lower sum and I still let the limit of as n goes to infinity be the one, or whether I take the upper sum, it does not matter whether I take whichever of the two, the limit will be the same, because remember, if we're letting n go all the way to infinity, we are getting really close to the actual area, whether from the upper side or the lower side. This should remind us of something we did, right? For limits, for the limit to exist, the number had to approach the same number from the left and from the right. So similar concepts, some of these concepts keep going. So that's the reason why. So definition for the area of a plane region. Let's see. Let's copy this one so you can let this play, and then just copy and then just rewind. Definition for area of a plane region. Let me highlight this. Let me make a nice big one. Yeah, there you go. Of a plane region. And what does it say? It says let f be a continuous function. This is really important. It needs to be continuous, because if we're going to be drawing all these little rectangles, we want to have the confidence that I'm going to be able to find a point as a height on each of these rectangles. Therefore, the function needs to be continuous. We cannot have no little gaps. And the other one is, it needs to be non-negative. For now, we're starting simple. We're starting on the positive, on the first quadrant, and our functions are going to be non-negative. They could still be increasing or decreasing. Non-negative just means that the f value is not going to be a negative number. We're going to come to that later, but not right now. Let's worry one little thing at a time. On the interval, you need to include your interval from A to B. Why do you need to include your interval from A to B? Because if your first rectangle is on the very beginning and you are asked to do a left point sum, then you are going to need to know a value of your function for f of A. If your function, if you're doing the right endpoint, for your very last rectangle, you're going to have to use B as your f of b for your height of your last rectangle. So that is why we need this criteria to be met. If this is not met, then this whole thing just I don't know. I don't even know what to say, but no, just don't. So the area of the region is bounded by, well, where's the upper limit? So you see what that says is we have a region. We're going from A, we're going to B, not drawn to scale nor to optics. Pretend that is a straight line. Do you know that in our regular Euclidean geometry, two parallel lines would never meet, but in non-Euclidean, which is called hyperbolic geometry, this could be two parallel lines. And that's why I got a really low grade on that quiz, I remember. And they meet, so all lines meet at one particular point or something close to that. It's been years. So hyperbolic geometry, it takes space. So if you've seen like that little thing, like sometimes like yeah, like fractals type of stuff, that's hyperbolic geometry. Hyperbolic geometry is really nice for modern geometry. There's a branch of mathematics called modern geometry, which deals with just irregular shapes. You know, like how scientists right now are coming up with new materials and new fabrics and all the stuff. So one of the really nice ones is the Taurus or something like that. Taurus. Uno de estos dos. This is the zodiac sign. Never mind. So it's this one. ESL moment. No, now we call him ELL, not English as a second language, because we're falling behind in the United States. We really need to learn more languages. But there's many people in the world that already speak 2 languages, so we just say, so it's a little bit egocentric to say, oh, you're an English language learner. Well, technically, if you're learning English, yes, right? We're like, whoa, I already speak 2 languages, 3 languages. You know, you cannot say I'm a ESL student, so we just call them ELL students. English language learners. But anyway, a torus is the famous donut. It's a donut shape, and then that donut shape is like you can invert it and stuff, and like the fabric without puncturing it, and like it's just really cool. I don't know what to say about it, but it's nice. So pretty much you have a fabric, right? A piece of fabric. How can you bend, rip, puncture, bring through the middle, cut through, or whatever without losing the properties of the fabric and stuff? That is what they do. Is topology. Topology deals with like the topology of a terrain. You know how it is on the bottom of the sea. This is the Loch Ness monster. It looks like a giant crocodile. And so this is the topology of the sea, the sea floor. Well, this is a structure. This is almost like a blanket and stuff. So when they send lasers or whatever to measure what it is, this go back, like the waves go down. There's a thing, the waves go down, and once the waves go down at this particular height, it reflects back. Remember, as it reflects back, they're gonna be getting back to the device at different rates. That the different time that it gets back is how high, you know, the wave found it and how fast it traveled back. So that's how we get these 3-dimensional pictures of the floor without actually studying it. Really amazing applications of that is happening in the Amazons right now. So many ancient Mayan and like just like old pyramids and stuff, and just whole cities are being found under the canopies of the trees because of this technology. Imagine all the treasures, all the gold, all the emeralds. Was that what they're called? Piedras preciosas, precious stones. There you go. But anyway, let's get back to this. Mathematics, amazing. So what do we have? We have an interval a to b, and it needs to be a continuous. It doesn't matter whether it's increasing, whether it's decreasing, whether it's just a constant. That is the most amazing one that we have, because then the area is just a rectangle. Or there is linear. Well, that's amazing too, because what do we have? If it's linear, look at that. You can say that this is a trapezoid. All right, this is what? Base 1, this is base 2. This will be my height if you just take this one and rotate it. It's saying that we need a function on the top, we need the x-axis on the bottom, and we need the region to be bounded. So essentially we're going from A all the way to B. This is the stereotypical, every math teacher, calculus, will probably use this graph to show, I don't know, maybe subconsciously we're thinking of pi. We are showing a graph that actually increases and then decreases and then repeats the movement. We're going from A to B because we don't want to start at 0, because then that will confuse some students, so we just generalize the case. But this particular drawing is widely used, so yeah, I don't know, I should make you more things. I don't know, I really wonder what kind kind of things you guys find interesting or would like to know about or have curiosities on. But anyway, so that means this criteria that no, you see, if life were that simple, just rewind. That'd be amazing. So we need the region to be bounded by the function, the x-axis, and the vertical line x equals a and x equals b. Please, everybody, please, please, please. I know that some of us are used to like, oh, if I give you y equals 3, like, oh, how do I graph it? I don't know, Mr. Perez. Mr. I gave my last name away. Jesus Christ. Y equals 3, we know that that is this line, right? Y equals 3. Like, oh, we're all happy, or f of x equals 3. And if I ask you to find from A to B, you're like, oh, from here to here, yay. But when I give students x equals 3, for a second they have to think about it and like, wait, what does he mean x equals 3? That's a point. No, it's saying give me all the points on this coordinate plane such that the coordinates are x equals 3. Well, guess what? 3, 0 is a point. 3, 1 is a point, 3, 2 is a point, 3, 3 is a point, 3, 4 is a point. So we have all these points and all the ones, all the real numbers in between. Therefore, how does the graph of x equals 3 looks like? Well, is this vertical line x equals 3. It is a graph, it is a line, it's just not a function. But it is a line. Please, we're going to be using this a lot now moving forward, from x equals a to x equals b. Actually, I really would like for you to just practice on your own a little bit. Just draw, you know, do the basic y equals 3, y equals x squared, y equals x cubed, and go from a to a b and just shade that region. See what that region looks like. Just create a nice little sketch drawing. Actually, you know what? I'm about to put that for your warm-up today. Coronavirus. Let's see. Yeah, and then so I want you to shade it. How does it look like from 0 to a b? And then I want you to show me how does it look like from a negative maybe 2 to 3. All right, that's and just draw it. Take a moment, let the video continue playing, and just draw, lower the volume, and take a deep breath. All right, it takes some time to visualize these regions, and it's gonna get crazier because now we have that two-dimensional region. Later on, I'm gonna ask you to rotate that around and keep rotating in three-dimensional space, and now we're going to get a nice little three-dimensional solid, and we're not going to be finding areas, we're going to be finding volume. So that's why it is very important to please be able to visualize these regions in two-dimensional space right now, be able to understand that we're finding this region by cutting rectangles, because later on in three-dimensional space, these rectangles are going to become discs. Remember, because this area starts being rotated, so they become instead of rectangles, we're going to be cutting it into nice little slices. That section, I love it because I always used to eat a lot of potato chips because it reminded me of that section with lots of Valentina and limon. Jam. And then I complain why my stomach hurts. But anyway, yeah, so let's move on. So what is the definition? Remember, we're still talking about the definition. Well, the area, we're no longer going to be finding like an estimate, like, oh, it's about this, but remember, oh, it might be an overestimate, it might be an underestimate. No more. Say no more. All right, area. What is the area? The area is going to be equal to the limit of what? Well, the summation from I equals n. Remember, we're gonna let n go to infinity. The summation of what? Well, the summation of all my rectangles. This is a rectangle. This is the area of a rectangle. Area of rectangle. Which rectangle? The ith rectangle. Any rectangle that you decide to choose. But remember, how many rectangles do I have? I have infinitely many. What is it saying? We'll multiply the height times the base. And we know how to find the base, b minus a over n. And we add all this up. But you see, if you notice, it's going to have something with I in it. All right. And what is f of ci? Notice that this is not even saying, oh, for the left endpoint or for the right endpoint or for the midpoint or blah, 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 blah. It's saying any ci. And where's my ci? According to this one, my ci could either be the left endpoint or the right endpoint, you see, it could be equal to the left endpoint, it could be equal to the right endpoint. It's saying that I can take my summation using the left endpoint, or I could take my summation using the right endpoint, or any point in between that interval. Theoretically, if we're letting n go to infinity, it does not even matter. Any of the points on the interval, if you let n sufficiently go to infinity, you're gonna end up with the area of the region. And what is that equal to? Delta x is equal to b minus a over n. So let's actually do a problem like this.